You can see my screen, right? Okay, Sanjita, are you here?
Yeah, I'm here.
Okay.
Shall we start?
Yeah, please go ahead.
Okay. So, good afternoon. We're here to share our final project progress for the course. So, I'm Sanjita Sarah Jennifer, and I'm working with Farhan Fuad Abir. So, we decided on the topic that hybrid diffusion model for ultrasound image augmentation, and we decided to look for the breast cancer BUSY dataset and see how and if we can implement and get good results with this work. So whenever it comes to the outline is pretty simple. We are just going to share the problem statement to give you some context of what and why we decided to do. We did our literature reviews in two parts, one for the breast cancer ultrasound and then for the diffusion model. So we will share that as we progress. And then comes the data set where we struggled a little bit and then finally overcame to get to the conclusion. Then comes the methodology of what and how we implemented and stuff. Okay, no, it's okay. You can. Okay. So whenever it comes to these sort of problems, we usually look at deep learning since they are more well known and work better with diverse data set. But we realize that in terms of medical imaging, the case is a bit different. So despite being safe, cost effective, and particularly prevalent and in low resource healthcare settings, ultrasound imaging datasets are a bit sort of limited. And the major issue is the class imbalance that we often see and which we personally faced as well, where the benign, malignant, and the normal cases were not equally represented that needed to be handled. So this affected the performance severely in terms of the generalization capacity and had to go through augmentation techniques such as rotation, flipping. We did our separate literature survey for that to see what works best for this sort of data set. And even for the GAN-based, the generative adversarial network-based methods, we saw that the realistic ultrasound features, they were not domain fidelity. So in contrast, diffusion model as seen in the last point have emerged as powerful alternatives. So that is something we wanted to explore and see. Especially in hybrid diffusion framework that combined text and images conditioning, which remained largely unexplored as we saw in our work while we were exploring. So that's what kind of motivated us to go ahead with this problem.
So I just want to have a quick reminder. We only have 10 minutes for each presentation. Okay, so we have like 5 minutes left. Okay.
Okay, so I'll skip through this because we know kind of why diffusion model. I have already explained that in that part. And I'll keep the literature review short as well. We did our literature review in few parts. And can you please go to the next slide? Yeah, so this is the image that I wanted to talk about. While doing a literature survey, this is one of the good papers that we found where the comparison between the ChatGPT 4.0 and the stable diffusion 1.5 was done. And we kind of followed this to see how our work differs from this one. Next slide, please. Okay, so this is the data set, and figure 2 represents the data, the samples, and it's publicly available. We can look at it, and we process this data set to go ahead with our work. Next slide, please. Okay, so this is just a representation of the how do I say it? The visualization of the data set before we started working on the model. So the class figure 3 shows the class distribution. Figure 4 shows the mean intensity by class, and figure 5 shows the height distribution to see if they were spread across evenly or not. So this is up until the point of the data set, and the next will be covered by Farhan Fuad Abir. Thank you.
Okay, so Sanjita, I briefly mentioned that we are taking a hybrid approach. So the main idea was sometimes in our literature review, we found that since ultrasound is a niche field, so when we only condition stable diffusion or fine tune it on the images with some text prompts, sometimes the results are not as good as the real images. So we were so our hypothesis was that if a separate step with image to image conditioning of stable diffusion does it improve any sort of performance or the generation process? So in short, we use first LoRa fine tuning to make it less memory intensive. We also used textual inversion to create textual embedding specific to ultrasound or domain. And lastly, we use control net so that the tumor edges are more consistent. So that was the three steps in phase one. And phase two, we used one step, that is to the image to image stable diffusion. So this is a very brief overview, like how we generated the prompts and how we generated the agents, and like the and we did two-step fine tuning. One was LoRa fine tuning, and second one was textual inversion to create the token embeddings. And finally, the image generation process looks like this, where we take the general stable diffusion model, and then we impose the LoRa weights that we fine-tuned, and also the token embeddings specific to our task. And lastly, we also use the control net to create to condition it on the edges, and lastly, image to image for further refinement. So we ran an ablation study of sort. So here the model performances, as you can see, this doesn't show anything extraordinary. These are pretty comparable with the real data set. And one thing to notice here is that the FID score, it's not terrible, but it's not very good either, but the trend is promising. With adding several components to it, the score eventually improves. So the generated images look like this. Here, just in contrast to the image that Sanjita showed, here after fine tuning, we can see much more fidelity or ultrasound specific image generation. Here are the steps and the classes, as you can see. And lastly, as I mentioned, the classification metrics are not very much are very much comparable. Nothing extraordinary going there. So our thinking behind that is that since the data set itself is not very much challenging, and the number of data is also very limited, like only 780 images in total. So that is not a very appropriate data set to evaluate this approach. So that's one observation we made at the end of the experiment. And also, since the FID score improved, so we saw potential behind our methodology, and also. Since the image style and tumor shapes are very consistent with the real images, so we found that the fine tuning actually is working. So in summary, we did a hybrid approach, and we evaluated in two types of metrics, classification metrics and also FID scores, which show improvement. But the main future plan with this method is to validate it on further diverse medical imaging domains. It might be X-ray or might be other ultrasound images, which might give us further insight on the overall performance. So these are the reference. So thank you.
Yeah, okay. Yeah, thank you for the presentation. So for the evaluation, you have these common metrics, right? Like the FID, all these. So do you also thinking about maybe using the generated data for some like downstream task, like using the ultrasound image to do some classification kind of thing? Because we want to validate, right, if the generated data is going to be helpful or not.
Professor, sorry, could you repeat the question?
So the generated data, right? So how this will maybe for like the breast cancer classification.
Okay. Okay, so let me clarify that. I had to rush through it. So in the real column, you can see I only use real images, and for real Plethora here, there's a inherent class imbalance. So I mitigated the class imbalance using the generated images. So it's like a mixture of both.
Okay, so you're using this to address the data imbalance. Okay.
Exactly.
Right. So,
exactly.
Okay. Yeah, I think make sure you explain this clearly, because I think I missed this part. I thought you're also just doing this for the FID. Okay, so it's pretty good to see that maybe some of the classes is making the improvement with the generated data. So it would be good to adding more visualization and also show some of the result, right? Which class, right? Because of the generated data, it kind of boosts the performance. You can have like class-wise accuracy, those things.
Yeah.
In the report.
Yeah. Sure.
Okay.
Sure, Professor.
Okay. All right. Thank you. Then let's move on to the next one.
Thank you. Professor, one thing. I might have to leave due to another schedule.
Yeah, so that's fine. Yeah. Okay.
Sorry. Okay. Thank you.
Yeah. Kathika? I think that's next team. Okay. Okay. Maybe you can mute your You can just share the screen. You don't have to connect mine. Yeah, because otherwise. Yeah, just share the screen. Okay. Yeah. You can do the present. Yeah. Yeah, okay. Please go ahead. We only have like 10 minutes, okay? Please be on time.
Okay. Hi everyone, good afternoon. Hi everyone, good afternoon. I'm Kartika Ramasamy and I'm working with Umema Khan. So today we are presenting our project, Dr. Doc, a multi-disease AI diagnostic platform for medical image computing. And the professor is Dr. Chen Chen for advisor. And what is the problem statement over here? So the main problem statement is like there are many patients are undergoing diagnostic tests every day. The most AI tools are built for just one disease here. So like when it comes to the realistic way, doctors must have to switch over each and every tool and they have to produce the results manually. So in that case, it slows down the diagnostics and also it increasing the false errors as well. So our project solves about the building Dr. Doc, a platform that uses the deep learning, and we are trying to see and give the results for 5 types of diseases using the medical image here in a one framework. The related work we got to know, we have chosen 5 types of diseases, COVID-19 and skin cancer, and brain tumor segmentation, and Alzheimer and lung cancer too. So the related work talks about the COVID-19 just classifies the full chest X-ray without the segmentation or attention in the existing one. And the skin cancer detection in ISIC just models the basic CNN, which is using a minimal amount of pre-processing thing. And the brain tumor detection, it uses a 3D segmentation, but it uses a heavy model, like which takes more time consuming, like the UNet and DeepMed. And Alzheimer detection, it uses a 3D CNN model, and it processes the full brain volumes, like which is not targeting on the specific thing. And also lung cancer, it uses a simple pre-processing in the CNN, but in the clinical explainability is really hard. And the limitations over that, what we discussed is, as I said, like its existing tools are trying to only for one disease, for like one time you have to take it up, the results. And it lacks in the real time. It will take more time too. And there is no integration of multiple modalities and models under the single framework as well. And our goal is to get the AI-based systems which detects the different diseases and using the deep learning models as well. And we are trying to make it as a deployable, user-friendly interface with a high accuracy and the explainability of each diseases. And what is the main motivation? Like, why to build the multi-disease platform? So in the real world, as I said, the diagnostic will take more time. It will, like, there is no more options too. So the multiple tests are expensive and that too the time consuming. So AI can speed up the screening and it reduce the clinical workload as well by using a simple and quick results. So our contribution is, like, we are using the unified diagnostic platform using the image here, and we created a custom and pre-trained architecture, and we are integrating deep learning models for structured inputs. Like, we are using different type of inputs for the 5 type of diseases, and we are doing a visual and quantitative evaluation. And this is a diagram that we created for it. So we are giving input of medical images, MRI and X-ray as an input, and we are trying to consult this 5 type of diseases, and based on that we will be getting the outputs like this in the great CAM. And let's see, go through it one by one. So COVID-19 detection, we are just using the input of chest X-ray images, and we are doing the required pre-processing thing like to enhance and clean the standardized images. And finally, we are detecting the binary classification whether the person have it's a normal or COVID-19. And if you see here, what is the difference? Like, because we are using the lung segmentation and SE attention to focus on COVID-19 affected regions. The previous one is not exactly targeting on the affected regions, so this is trying to give the attention over that regions. And next is skin cancer detection. It uses efficient net model and custom CNN. This also processes the same way of input and required pre-processing. And this difference, like, we applied the low contrastive thing, like to concentrate, like if it is a image or low contrastive, then we are just trying to manage that as well and performing required augmentations and all. Now I'm giving over to Umaima to continue.
Hello everyone, this is Umaima. So for the brain tumor detection, we used a fine-tuned VGG16 architecture enhanced with soft spatial attention. VGG16 is known for its deep convolutional layers and is particularly effective in learning local spatial features. So, however, to increase its sensitivity to relevant tumor regions, we integrated a spatial attention module. The input to this module is an axial T1 weighted MRI slice, which was resized to 224 by 224 pixels. And for the pre-processing, we applied skull removal using tools like FSL BET or thresholding to eliminate relevant bone structures that might confuse the model. And after that, we normalized intensity and performed data augmentation techniques such as elastic deformation, intensity scaling, etc. For the Alzheimer's detection, we went a step further and we used a 3D model that can look at the brain scans as full volumes and not just slices. So this is important because for Alzheimer's, Alzheimer's show up in different areas across the brain and not just one. The scans go through some cleanup first, then we fix lighting issues, remove the skull, line them up to a standard format that brain researchers actually use. And then the model looks for patterns that match different levels of dementia, from no symptoms to moderate ones. For slide 14, our lung cancer model, this looks at the chest x-rays. Before sending them into the model, we sharpen the image using a method called CLAHE, Contrast Limited Adaptive Histogram Equalization. And we apply filters to clean up the noise. This model is simpler but still accurate. So it just gives us a clear yes or no answer, like cancer or no cancer, and it's fast and efficient way. To train our models, we used real publicly available medical data sets. For the COVID-19, the data set has chest x-rays from COVID positive and normal patients. For skin cancer, we have dermoscopy images showing benign and malignant skin lesions. For brain tumor, MRI scans labeled with tumor presence. Alzheimer's, full brain MRI volumes across different dementia stages. And for lung cancer, normal lungs in cancer affected ones. So we trained our models using powerful tools like TensorFlow, scikit-learn, and we use 70% of our data for training, 15% for checking along the way, validation, and 15% for final testing. We used accuracy, F1 score, area under the curve, etc., and we also use cross-validation. For the qualitative results, we've mainly focused on GradCam visualization so far. So these are the heat maps that show exactly where the model looked when making a decision. For the quantitative results, the performance is mixed. COVID and brain tumor are our best performing models, and skin and lung cancer have low F1, maybe due to some misclassifications, and Alzheimer still needs to be worked on, especially for the early stage cases. So we're almost done with the work, but what's left now is we have to build a clean UI to integrate everything in one, and we have to make sure that all 5 models work together in one place. We also have to work on the Alzheimer's accuracy and connect everything with a backend. So to conclude, Dr. Doc, it proves that it's totally possible to put several disease detections in one simple platform. And going forward, we plan to add more data to improve the accuracy and let the system detect multiple diseases at once, like if a patient has more than one condition. And we also plan to integrate both imaging and non-imaging data as well, like lab results, symptoms, patient history, etc. Because doctors don't just rely on one modality, they also need other information about the patients in tabular or clinical format. So that's all about it. Thank you.
I think the big takeaway is you guys want to design a simple UI, right, to integrate all these different models, right? Well, I'm interested in what that UI look like, right? How
It is like a simple display, Professor. We have already trained with all these models. In case, for example, if we give one type of image and it will pick for, like, we will select which disease we wanted to look over, and then it will pick. We will give an input on it, and it will select that disease, and it will process everything, and it will give an output for it.
So from the technical point of view, you guys don't propose anything new, right? So because it's just off the shelf models for different.
No, we are proposing. In the related work, we pointed that they used some lesson. I'll show. We are trying to add the informations in the models, Professor. Right? Here. So if we see the COVID-19, the paper which we are referring, that classifies the full chest X-rays without segmentation and attention. But what we try to do is we are trying to do the separate segmentation using a unit which will just focus only on the required area, which will give us a quick response as well. And we are performing the SE attention too. It's same way we are doing two different changes in each models. In skin cancer, they already performed on basic CNN and ResNet with a minimal processing. But we are trying to do more, like we are trying to, in the skin demographic images, if there is any hair or something else, so we are trying to remove that too, and we are making the changes into it. The brain tumor is also same way. So for same way we are doing the changes, Professor.
Platform, there's gonna be a lot of like data processing, all these. So do you, for like a doctor easy to use, then basically they don't have to do any, handmade or man-made, these processing. So are you able to take care of all these kind of pre-processing
What is our first thing is it's not directly deploying into any web server like Docker and all. So before that, we are planning to make an IBONB, like just try to implement that over here. I have seen the option like we can make all saved the trainable models to reusable, and we can put it into the single platform like a particular one POI file, and we'll try to call the models and we can try to get the outputs, and we can do like if needed we can do different user friendly UI design, otherwise we can make a simple design, so and that's preferable.
Yeah. Okay. So yeah, I'll be interested to see the final product, the UIs, how easy to integrate and also expand different models, right?
Sure,
So,
sure.
Because we can keep adding models, like keep adding data sets.
Yeah.
Okay. Okay. All right. Great.
Thank you.
Okay, so we have, let's see, the next team. Brian?
I'm Alejandro and Brian is on Zoom.
Oh, okay. So you want to
I'll share.
share the screen?
Yeah.
Okay. Okay, all right.
Ready?
Yes, go ahead.
All right. Hello, everybody. Oh, let me get the microphone. Hello. Hey, so my name is Alejandro Parcedo. My teammate is Brian Garcia Rodriguez. He's on Zoom. And this is our project, simultaneous nodule localization and classification in CT using the LIDC IDRI dataset. Right? Okay. So the outline real quick, we have our problem first. I'm going to explain it, the motivation, related work, data set, methodology, result, and conclusion. Before we move on, I just want to make sure that Brian has his microphone on. Are you there?
Is he online?
I saw him online right before. I'm so sorry. 1 second. Brian?
Yes, can you hear me?
Yes, now we can.
Okay. For some reason, my mic was having issues, even though the sources were correct. So I apologize for the technical difficulties.
Yeah, it's okay. Let's move fast.
To begin, so the main objective of the study is to develop an integrated framework for simultaneous localization and classification for pulmonary nodules in CT scans. Some of the key challenges were difficulty accurately detecting small nodules, as you're going to see further, and a high rate of false positives in nodule detection, plus the need to integrate pipeline to streamline diagnosis. Good. So within clinical relevance, lung cancer is one of the leading causes of cancer-related mortality globally. And early detection would be one of the most significant ways of stopping for further treatment. Identifying and classifying nodules early would be tremendous, and allowing for clinical intervention. Limitations of current diagnosis methods would mainly involve highlighting the necessary advanced automated systems to improve accuracy and efficiency, as you'll see further along, including attention units and some other methodology. Some other related works include deep lung, which primarily focuses on localization, though it does not have robust classification. Attention units, which I'm sure most know, multitasking frameworks.
Brian, we're going to skip the related work.
Okay.
Thank you. All right, so for the data set, like I said, Lung Image Database Consortium and Image Database Research Initiative. So that's the name of the data set. This data set has around 1,000 images. It contains X-ray, CT, and CR. So for our case, we are focusing on CT, so we're filtering for all the cases that have CT. And also, only 158 of the 1,000 patients had a final diagnosis. So we are also focusing just on those. And this is what the data set looks like here. It's the CT image with the ground truth mask. And all the volumes are resized to the shape 256 by 128 by 128 as they're processed through the neural network. And talking about neural networks, so our model architecture, we have a two-stage framework that is end-to-end, so that we have a single gradient flow all throughout the network. So we have a 3D attention unit it's focusing on segmenting the nodule volume, the voxels, and then all the bottleneck features from the unit are passed into a classification layer, which will segment it as benign or malignant, or these are all the classes. And then for our training details, we have a weighted dice. Why weighted? Because there is a severe class imbalance between the number of voxels that are background and the number of voxels that are nodules. It's something like 1% nodule versus 99% just background, so very severe. Optimizer, we use Atom, and then for the scheduler, it's cosine annealing. So as we can see here, so we have our training loss and validation loss going down, but from our actual results here, let me move this. So this is our mask, and this is our prediction. So our model is reducing the loss somehow, and it's cheating on the predictions because, of course, it's just covering the entire area, and it'll be in here because all the nodules are going to be in that section, but it's not really right. So if anybody has any suggestions on how to improve this class imbalance, that would be very helpful. But yeah, that's what the predictions look like right now. And this is just one slice taking out of a volume. So each prediction will be an entire volume being predicted. And then for the conclusion.
This integrated framework offers potential improvements over existing methods by effectively combining advanced segmentation with robust nodule classification. Future research will validate the proposed framework extensively and explore enhancements through additional context-aware techniques, including supervised learning techniques, self-supervised.
Thank you. So we have references and open for questions if there's any.
So do you use any pre-trained model? Because I think your result pretty much doesn't learn anything, right?
No, so it's not pre-trained, no.
So have you used any pre-trained model because you have limited data, right?
Yes.
So right now, you train from scratch, seems like the model doesn't learn anything. Did you check the ground truth label, like everything's correct? Why is basically doesn't predict anything?
Yeah, so I did check.
Make sure like the data loader, the segmentation mask is loading properly, right? You're not loading anything incorrectly. Then the model just basically doesn't train anything.
Mm-hmm. Yeah, so I've checked a couple times. It is possible there is still something in there, but it's kind of been a process trying to figure out what the mistakes was. So what my intuition is that it's mainly related to the severe class imbalance because the model can just predict background.
How surveillance, what we are talking about?
So out of all the voxels in the data set, only 1% is masked, like a nodule.
Yeah, but if you look at other data sets like brain tumor, I think the last team doing the brain tumor segmentation, it's also only occupy a very small region and different, across different sizes. But I don't think that may cause, because right now the model is basically doesn't predicting anything, right? So
Yeah.
So it means that that doesn't even learn anything, any pattern related to the nodule. So you may want to check that. And do you do the data augmentation, all these things?
No, so no data augmentation because we just wanted to get like a.
Yeah, so I think later I think a couple of suggestions for you guys. One is make sure there's no small mistakes, like the data or the mask loading correctly, so the training data and the annotation pair is properly, right? The second is try a pre-trained model, right? So train from scratch with limited data may be a little bit, challenging, right? And also you have data imbalance issue. So some of the like weighted dice laws, these are the good choice because you have this imbalance issue. But also try some data augmentation strategies, right? And see if that will also help. So I think all these, well, you need to basically babysit the training process.
Yeah.
So otherwise, won't able to get some good result.
Yeah. I agree with all you said. It's just it's planned. The only thing that was confusing to me, so initially the loss was pretty much not learning anything. It wasn't going down at all. And then after we implemented like the weighted dice, for example, and then changing the optimizer, then we started seeing the loss go down. And instead of being complete like prediction being like all the same all the way, it started identifying like this area as the one that's where the nodules would be. So I guess that's where I stopped babysitting, and then I had to present it here. But yeah, all those things are planned. Yeah.
Okay, so yeah, I think you guys.
Some of the recommendations is focal loss for instances where there's huge class imbalances, and then I guess the next steps would be data augmentation.
So by the way, also
Would probably have to be either.
Is
There's also the method of slicing the images instead of the whole image.
So we didn't try 2D version because that's been done before, specifically with this data set. So we wanted to see like, would using the volume and having the spatial relation between the slices.
2D, 3D has been done, not necessarily for this data set, but it has been used a lot in medical data. But just to help you to at least gain some insight, right, or get the correct or reasonable result, maybe you can also try the 2D version, right, slide by slide, and see if that also help. Maybe you can later do like a comparison, right? So at least maybe you have one option that is working properly.
Okay. Yeah.
Okay.
Sounds good.
Okay. All right. Thank you.
Wow. Thank you.
Okay. All right. Thank you. Right. The next team. Okay. All right. You also in the Zoom? Mm-hmm. Okay. Are you in the Zoom?
No.
You should
Oh,
join.
I should
join
join the
the
Zoom?
Zoom. Then you can share the screen. Yeah.
Just a minute.
Do you find the Zoom link?
Yeah.
Okay.
I'm just joining. Just. Oh, okay, my bad. Yeah. So. Just a minute. So yeah, hi, good afternoon everyone. I'm Anirudh Narasimha Bharadwaj, and I'll be working on this, a panoptic approach for melanoma histopathology, that is nuclei semantic segmentation and tissue semantic segmentation and nuclei instant segmentation. So now this will be the outline, the problem statement, baseline, and you can just go through that. So here the data set I'll be using is the panoptic segmentation of nuclei and tissue in melanoma, that is Puma. That's a grand challenge, open up. So I'll be using those data sets. The training phase has a total of 205 images, that is 103 metastatic images and 102 primary images. So with that, and they are at 1024x 1024 at 40 times magnified. So that is the data set we'll be using. And the goal, is to segment 6 tissue types, and that will aid to the localization of the nuclei, which is having 3 types, that is tumor infiltrating lymphocytes and others. So there are basically 10 classes in the nuclei, but we'll be reducing it to the 3. That's what the track 1 suggests. So that is the thing. And there's a severe class imbalance, which I'll be addressing in the later slides. And clinically, why this is required? Immune checkpoint inhibitors are effective, but it's just 50% efficient, and it's very costly and toxic as well. So that goes as per the studies, like clinical studies. So that is the need for segmentation. So going on, we have 2 tracks. That is this one is the baseline. So here they have given the NN unit architecture for semantic tissue segmentation and HoverNet for nuclei instant segmentation, where HoverNet doesn't, they haven't specified the metrics here for the HoverNet, but the die score for the macro dice for tissue is 0.629, that is 62%. So that is the thing they have given, that's the baseline. And the limitations of this is, as I told, there's no class weighting on this thing, and whatever they have given is dockerized, and the weights are provided for the reproducibility. So, and the source of the thing is also provided there. And going on next, this is the related histopathology studies that are going on. HoverNet is a very specialized model for nuclei instant segmentation, and Mars-CAR-CNN is what I'll be proposing. So going on next, I have mentioned that paper as well. NN unit is dynamic model for semantic segmentation, so that is also there. And Panoptil, this is an approach which uses the Panoptil dataset for panoptic segmentation of breast cancer. So that is the thing. MaskFormer is also used for panoptic segmentation, but there's a drawback for this, because in medical imaging there's a challenge that the data set is very unique, and the scalability is very different. The tissue size and the nuclei size is very different. So single model with 2 branches is very difficult. So what we'll be doing is, so this is the thing, panoptic segmentation of combining the 2 tasks, and the major research gap is the current methods focus on separate tasks. That is one model with 2 branches for nuclei, that is the stuff and the things. So that is how it works. But we'll be implementing a 2 pipeline model, and as you can see, I have given the class distribution as well, which is very severely low. So that is the thing. The outline goes like this. One, I'll be planning, I'll be doing this stuff. I'll be negating the class imbalance by oversampling the patches. Synthetic generation is overruled because this is medical imaging, so there's no point in generating pixels. So that is one. So I'll just plan to oversample the patches, and the 1024 patches is divided into 256 with a stride of 128. So we get 7x7 in a single image. So that is how it works. And evaluation metrics, I'll be using the panoptic quality for nuclei, Jacquard, and macro F1. Tissue, I'll be going with micro dyes and macro dyes. So both the things I'll be using. Mask RCNN is what I'll be using for the nuclei instance segmentation, and SWIN unit for 6-class semantic tissue segmentation. The mask RCNN part I have completed, and the SWIN unit, it's at a very preliminary stage. I'm starting it. I'll just show you the results in the later slides. So the last one will be the merge outputs in a GeoJSON format, and the dataset they have given is also in the GeoJSON format. So the panoptic mask will be in that. The data is loaded like this. Data processing is done. We extract masks and create patches with stride 128. Pipeline, I'll be using the 2. That is the thing. And going on next, why this 2 pipeline thing works? Because mask RCNN, that excels at instance segmentation, because it is having feature extraction and the RPN part, that is proposal network, and the classification at the last, which is having the 3 heads. And so that works very well for instance segmentation. So that I thought I'll be bringing that into the medical aspect of nuclear segmentation. And the pros and cons are there, but it's a very good approach, I thought. So that is the thing. And yeah, so as I told, this is how the data processing looks. And going on to the mask RCNN, yeah. So first I implemented using binary, that is tumor versus non-tumor, to get just the binary logits and other stuff to validate the pipeline, if it is working or not. Then I moved on to the 3 classes, the tumor, others, and tills. So the configurations.
I think you don't have much time. So
I'll just rest through it.
Do you have other results?
Yeah, I'll just show that. As I told, SWIN unit is at a very preliminary stage. I've just showed the ground truth. So moving on, the classes are really rare. So I'll just go to this is the parallel execution part, which I'll be doing in the further stage, that is after the SWIN unit completion. So we'll be getting instances like this from the mask RCNN part. This is the debug image that I have put here, where the instances are in 1001s, 2001, and 3000s. So that is the thing. And this matrix is at a very primary stage of mask RCNN, and it's training still, so I couldn't get the last one. But as you can see here, the macro F1 is 66, which is quite low, but it is in the very early epochs. I did a validation at a very early epoch, that is the 3rd epoch of the first fold. I am implementing a 5-fold cross validation, so that is the thing. And these are the results after some time. So the first one, binary part, the binary logits versus the ground truth. So, and the second image you see there of the nuclei, that's the output mask generated. There's this and the tissue part, as I told, it's at a very preliminary stage. I'm starting it right now, and the severity of class imbalance is so high that it's very much struggling to learn. And I'm using a weighted dice focal for tissue segmentation. So I'll come up with something for that. I'll come up with a class imbalance thing. And
So yeah, you can skip this. Can you go back to the previous slide?
Mm-hmm.
So why you have ASEAN, swing unit,
Hmm?
panoptic segmentation. Like, what's the purpose of these three methods? You have three tasks.
We have two tasks. We have one task, that is the panoptic segmentation. So panoptic segmentation is instance segmentation and semantic segmentation.
So, like, what are you do the comparison between these three methods, or like?
No, in melanoma, what happens is the biomarkers are very important for like
Yeah,
the.
tell me, like, what do you use these three methods?
So basically, I'll be merging the outputs of semantic and the instance segmentation, that is from the SWIN unit and the mass Gaussian. I'll be passing it to I'll be using the NN data parallel thing on two parallel GPUs. I'll be passing it to the, I'll be adding up the loss and I'll be back propagating it. So I'll get a single patch with both the segments.
To make the, the motivation clear, right? Because right now I don't understand, like, why do you need the three methods and how you are using three methods. So
Panoptic FPN is used for panoptic segmentation. Generally, panoptic FPN is used. But the thing is, there's a heavy scalability factor that comes into the picture here. Like, if you're doing it in a general environment, people versus car or something, that is, the panoptic FPN handles it very well. But at a medical imaging thing,
tried it already? Like,
yeah, I got a very low.
you need to show that motivation, right? So if you're using some panoptic segmentation directly to the medical image, they may fail. But do you tune or do you fine tune these using the data? Because I don't think you will, if you do some fine tuning or training, you should be fine, right? But right now, I feel like the motivation of doing this is not that quite clear. Like, you are using these different type and method to merge the result. Those things you need to explain that very clearly in the report. Okay. So otherwise, people don't know, like, why you are doing this. Okay.
Yeah, I got that.
Okay. All right.
Yeah.
Can move on.
Thank you.
Next one. Are you next one?
Yeah.
So, do you have your
I have submitted my presentation slides. Can I present to your laptop?
your name?
Fahim Sakai. I think I mentioned the UC file since 9.
F.
Yeah. Fine.
This one?
Yeah, this one.
Okay. Okay.
Thank you. Hello, good afternoon, everyone. So I'll be presenting my work on cryogenic electron tomography 3D particle detection. So my objective was to propose a model called CryoSam2, which will be based on a published paper on last year in MICAI. So it was CryoSam1. So the problem is that so cryogenic tomography, it's in simple terms, it's just like 3D voxels of what is happening inside our cells. So the physicians, they want to know how our proteins in our cells, they react to different external factors to develop medicines and etc. So the problem is, till now, we haven't figured out all the proteins that are present in our cells. And even the proteins and the filaments and those macromolecules in our cells which are visible to our human eye, we haven't been able to annotate all of them. So right now, in cryogenic electron tomography, the main problem is we need to find an efficient way to annotate all those known and unknown macromolecules. So in this diagram, you can see that like pre-processing and annotation, the pre-processing takes comparatively less time, but annotation and then reconstructing it into 3D structures takes a lot of time. So we need to like efficiently do this annotations and the reconstruction part. So this is a sample image of what the tomogram looks like. So it's most of them are noisy. So a lot of macromolecules are not visible to the human eye. So and these are in like this comes in different formats, those tagged image formats and MRC files, star formats. There are a lot of them, and there are a lot of like softwares like Railian, CryoSpark, which are used to pre-process this. So in my experiment, I used two datasets. One is MPAIR 10499, which is a 65 tilt image of pneumonia viruses in the cells, and a defocus ribosome dataset, which is the 3D tomograms from which we detect the ribosomes. I think this was an just okay. Let me skip over this one. Oh, all right. So I just like added how it looks if we go through the slices. So this, I think this won't work right now because it's linked to an video that I uploaded. So moving on. So most of the work that has been done, what they do is they consider those 3D boxes as 2D slices. And there are a couple of published models that that take those 3D voxels as 2D slices and processes them. And one of the well-known one is the Cryolo, which is a CNN architecture-based model. And I used that on my data set. And initially, the left one shows the result that I got. So there are a lot of overlappings. So after like implementing the non-max suppression to like remove the detections that are common, so this is the one that I got. So, but as you will see, the result is not really that satisfactory. So the first one shows the evaluation metrics before non-max suppression, and the later one shows after I have implemented the non-max suppression. So the difference that you can see is the false positive rate. It decreased a lot, but still the scores, the precision recall and F1, they are not like up to the mark. And you'll see that in the published work, they also show that even if in best performing models, it doesn't go over like 50%. So, and one more thing I'd like to draw your attention to is that we will be focusing on the recall part, because when it comes to detecting those macromolecules inside the cells, we are more concerned about the, we don't want a false positive because that would be more detrimental. So we kind of put a lot more weight on the recall part. So hence, we also like focus on the F1, basically the F scores. Okay. So the paper that I talked about, which was published last year in MICAI, so they proposed a CryoSem model, and you can see they have also compared it with the Cryolo model. So the Cryolo model, they use 100% of the annotation. So here what we do is we take a specific tomogram and all the annotated points associated with that tomogram. So in this paper, they used the 100% of them. So in my experiment, what I did was I used around 25% of the annotated tomogram corresponding to a annotated points corresponding to a specific tomogram. So for that 25% of the annotation, I got the results that I showed earlier. But in this case, even if they use the 100% of the annotation, you can see the recall, precision, and the F scores, they don't like really go over like 50%. And in case of CryoSem, they kind of do better, not by much, but they do better by using 5%, 10%, 30% annotation. So yeah, moving on. So this is the CryoSAM architecture. So their pipeline has two-step process. One is they use sorry. Yeah. So they use encoders from Dino V2 developed by the Facebook, and they also mentioned that the Dino encoder performs better than the SAM encoder, and they use the encoder to extract the features, and using those features, they performed a novel hierarchical feature matching. So in simple terms, what they do is they take the predicted feature mask and then use that mask and perform an average pool and perform a iterative cosine similarity. And the main idea is that a particle in a 3D space, a particle in a 3D space, they will have a cosine similarity in corresponding slides, or the slides which are adjacent to each other. So they did an iterative cosine similarity and then perform a non-max separation. So what I want to do is I want to perform a comparative analysis by replacing the Dino V2 encoder with the recently proposed SAM V2, and also I'm looking into how I could go about optimizing the hierarchical feature matching. So, and the technical difficulties that I am facing is that this CryoSAM pipeline they have proposed, it cannot be executed in even GPU of 16 or Newton V100. Yesterday was the first time I got hold of the H100 and I could run the entire pipeline. And the second thing is that I am facing a bit of problem regarding the tomogram processing, because it requires a lot of computational biology knowledge, and the tomogram processing tools such as REB, those are designed for 16 GB plus GPUs. So it is a very resource intensive program. So yeah, these are the references, and that would be all. So if you have any question, you're welcome.
You may have challenge to finish the project, right?
Sorry?
You are facing several challenges to finish the project.
Yeah.
So maybe you should switch to a smaller model, right? The SAM, which is also a large model, SAM V2. Just like the last assignment, maybe you can use some efficient or small model.
Yeah, I could.
So
yeah.
I don't know why you want to using a huge model, like even Newton H100. You said you're not enough.
No. Newton. I can run this one on Newton H100. I can do it on V100 or GPU 16, and I can get more than one node.
You can always get H100 from Newton.
Yeah.
So that's the issue. So you may seriously want to thinking about the computing if that's the main bottleneck for your project.
So I was thinking as I mentioned, I will be modifying the encoder part. So maybe I will try to include the efficient SAM or.
Don't tune the part, right? So because if you have you need to fine tune or train a large portion of the model, then that's gonna be the bottleneck.
No, here's the thing. This one, they don't require any sort of training. It's they take the So their main contribution was the hierarchical matching part. So they use a pretend SAM network or Dino V2, and then in those are 3D voxels. So they prompt the SAM for all the six coordinates, coordinates in 6 directions, the X, Y, Z in 6 directions, and then they take it and then they perform a hierarchical matching using a cosine similarity to find all other non-annotated points.
Yeah. Okay. All right. So I think you may have to thinking about the computation, right? So because you have maybe a week or two to finish everything. Okay.
Okay.
Okay. All right.
Thank you.
So we have one more team left. Is that correct? Okay. All right. So are you using your computer? Yeah. Okay. Are you join the Zoom?
Yes.
How are you doing? My name is Lam Nguyen. I'm a computer vision master student, and this is for Maz Abu Talebe.
I'm doing Master of Computer Vision too.
All right. So our project is we're going to be benchmarking different CNN networks that require low resource usage to do brain tumor MRI imaging scans. So brain tumors are very life-threatening, and early detection is really crucial in helping to save lives. Actually, manually interpreting a lot of these images is very time-consuming. It's prone to human error. So stuff like this is actually very perfect for AI.
Yeah, this test is more complicated than it sounds. The problem is that different tumor type often looks visually similar in MRI images. Even trained radiologists can find it difficult to tell them apart. In our data set, we had 4 classes: glioma, meningioma, pituitary tumor, and no tumor. Sometimes the edge of tumor blend with the surrounding brain tissue. Over time, 2 tumor type can appear almost the same in the grayscale image.
All right, so some of these are related work, so we won't go over them for time. But our motivation for this project?
Our main motivation was to explore how well different CNN models perform on classifying brain tumor. This isn't just a machine learning challenge, it's something that can impact real-world healthcare. If we can train a model that consistently gives over 90% accuracy, especially with high precision and recall, it could help reduce human error and speed of diagnosis. We also wanted to build a reusable pipeline. The goal wasn't just high accuracy, but the reliability and confidence.
All right, so our main contribution, we want to build a reusable pipeline to pre-process, train, evaluate, and visualize results. We want to have a pipeline where you can just input different models. So we have, for now, 4 deep learning models that we're going to be using. And then from those deep learning models and training, we want to create visualization, which includes confidence scores, PR, ROC curves, and to show misclassified images.
Here is a quick overview of our pipeline. First, we loaded and prepared the dataset and applied pre-processing like resizing and normalization. After that, we trained 4 different models: VGG16, EfficiencyNet B0, ResNet 101, and Exception. Using the same training and validation split, each model was then evaluated using metrics like accuracy, F1, precision, and recall. We also looked at the misclassification. So far, we analyzed ROC and PR curves and confidence level for VGG16, and we are planning to apply them for other models. Finally, we compare the result to see which model performed best.
All right, so I'm going to give a quick overview of our data set. So it's, of course, brain imaging scans, 7,023 images, 4 categories: glioma, meningioma, pituitary, and no tumor. You can see from the diagram that there's a relatively even spread of data. There's no imbalance, class imbalance. So we resize to pre-process the images, we resize them, we normalize them, we enhance their contrast, and we enhance their brightness. And for Maz, he's going to discuss in the 4 models that we tested and why we tested these particular models.
We started with VGG16, which is a classic convolutional neural network. It has around 21.5 million parameters, which is quite a lot. To make it more efficient, we froze the early layer so it wouldn't be retrained. Next is efficient net B0. It's the smallest model we'll use with only 5.37 million parameters. Despite being small, it performed very well. The model is especially useful in situations where you want fast prediction with lower memory usage, for example, in mobile or embedded system. ResNet 101 is a deep model with 42.66 million parameter, making it the largest one we tested. It uses residual block to solve the vanishing gradient problem. We chose it because its depth and high capacity often leads to a strong performance on complex image tasks, especially in medical imaging. And exception uses the depth-wise separable convolution, which help reduce computation while keeping performance high. This balance of size, accuracy, and reliability is why we chose exception. And here is a summary of what we said, but as our time is limited, we skip this part.
All right, so our training setup, we kept everything standardized across all the models that we're training. So 90% training, 10% validation, batch size 32. We trained each model 15 epochs with an atom optimizer and cross entropy loss. We kept that standard. So we tested our evaluation metrics or the accuracy score, F1 score, precision, and recall. And for visualization of the data and the training, we use the confusion matrix, ROC, PR curves. We show you misclassified images so you can get a feel for it. We also showed confidence histograms and top K accuracy. These are some of the data, the visualizations that we generated. We won't go over them too much.
Only for VGG16.
Yeah. However, one of the things that's interesting was with the confusion matrices, where you see like the false negatives, or basically where the model is saying that a person is healthy when they're not. I would say this is actually a pretty important thing because you don't want to say somebody's healthy and then they end up dying. For EfficientNet, it had one false negative. ResNet got 0 false negatives. ExceptionNet got 1 false negative, and VGG16 got the most false negatives at 3, meaning it said 3 people were healthy when they weren't.
This table shows the full comparison of all models based on key metrics. Exception had a F score of 0.99, so that efficient net B0. Both also had precision and recall values of 0.97 or higher across all classes. ResNet 101 followed closely with 0.98 accuracy, with a slightly lower recall on some classes. VGG16 had the lowest score with a F1 score of 0.97 and drop in precision and recall. This table confirms that exception is not only the most accurate, but also the most balanced across all classes. However, EfficientNet B0 uses only about 5.37 million parameters.
So this is a summary of our results. I won't go over them too much. However, one of the things that, like, for me personally makes it unclear which is the best is that ResNet, although it uses the most computing resources because it has the most parameters, it also had 0 false negatives. And I would say, even though the other scores are higher, like the accuracy and F1 scores might be higher for the other models, the false negative thing really comes into account because you don't want to say somebody's healthy when they're not. So which one is better for me, I'm not quite sure at this point. Oh, and what do we have left to do? We want to be able to visualize the results and also the data more. We want to show the confidence distribution, and we actually want to show the misclassified examples for each model. We have it for some, but not all of them. And also, eventually, we want to kind of streamline this pipeline and create a web-based tool for radiologists or just patients or anybody in general. So
to sum up, we built a full system that compares 4 deep learning models for brain tumor classification. We trained and tested each model on the same data set to ensure fairness. in the end, exception showed the best overall performance with 99% accuracy, only 9 misclassification, and very high precision confidence. Our pipeline is also generalizable. It can be adapted for medical imaging tasks. In the future work, we plan to evaluate more model and add explainability feature for doctor and even test real-time MRI input. But before we finish, we'd like to ask you, based on everything you've seen today, let me go to the table. Based on everything you've seen today, which model would you consider the winning model? Exception had the highest overall metrics, but it misclassified one tumor as no tumor, which is risky. ResNet 101 had no such mistake. VGG16 had 3, and EfficientNet had 1. Thank you.
Yeah.
You can also add like something to like the number of parameters or something that shows like which one is the more lightweight, because the performance seems very simple.
Yeah, I actually thought about that when I saw that paper, that we should have added a table for GPU usage or parameter usage.
Like a proxy for like model size.
Yeah. So.
Yeah, but I think for the clinical, as you mentioned, right, you don't want, people actually has tumor, but end up diagnosis, this is, normal, right? So then, in that sense, then the ResNet 101 is definitely, if you want to look at the false negative, right? So you definitely want 0 of them, right?
Yeah.
Because you can spend, more time to figure out, if it's going to be false diagnosis, but if you miss it, then people forget about it, right? So in that case, that's the sole priority, that you need one model that's produce 0 false negative. Yeah.
But also, I'm not quite sure, because sometimes you can retrain something multiple times, and sometimes the results change.
Yeah.
So I don't know.
Okay, so I think you guys, need to. I'm a little bit concerned about what is the biggest takeaway from these experiments, right? It's good that you have different models do the comparison, but what is the biggest takeaway from that, right? So if you want to suggesting something, right? So what is the message here?
We left that open to interpretation. I mean,
yeah, but you guys have to think about this, right? So with these experiments,
for me personally, I would weight the false negatives higher when it comes to actually diagnosing patients. So ResNet would be worth the trade-off in extra computing
also
power.
Things, right, like, why choosing these 4 different models, then if the resource is also something as a limitation, right? So can you substitute, or is there a small model or efficient model can perform very similar? I mean, achieve maybe the 0 false negative, but the accuracy can a little bit lower, but you have the benefit of very efficient and also have maybe like 0 false negative, right?
Yeah, we're still looking into that. EfficientNet used 5.37.